With each fascinating picture captured by the James Webb Space Telescope, it keeps on getting thought from various corners of the universe, including planets within our own planetary system. A year earlier, we pondered our introductory brief glance at pictures showing the Carina Cloud-Stepan Quintet and, strikingly, the enchanting Deep Field image. This particular picture apparently portrays different universes stretching out into the colossal region of the universe, fulfilling the assumption created. The James Webb Space Telescope hasn't stopped surprising us. It has recently revealed objects that challenge established cosmological ideas. These puzzling discoveries are now marked as universe breakers by cosmologists, confusing the scientific community with their ability to go against existing ideas. The reasons behind these revelations remain shrouded in mystery, throwing our conjectures and hypotheses into disarray. So, what's the latest scoop from the James Webb Space Telescope? What incredible, eminent information has it uncovered that was previously unknown to us? Join us as we dive into the revelations of how the James Webb Telescope has presented evidence suggesting the existence of another universe, challenging the traditional perception of the Big Bang. Our universe, as we have long understood, arose out of a hotter, denser, and more uniform state, past a thought known as the Hot Big Bang. This speculation, a critical scientific accomplishment over the past century, found dazzling endorsement during the 1960s with the discovery of the cosmic microwave background, a remnant from the early hot and thick state. Over time, the Big Bang has remained the dominant theory explaining our cosmological origins. However, new and crucial observations have led cosmologists and astrophysicists to question both the infinite expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain momentum, highlighting the persistence of the theory of the Big Bang. According to the prevailing view, the description of the universe's origin involves a smaller, denser universe in the distant past. The presence of radiation like photons shows that the universe was hotter at its origin and has since cooled. By extrapolating backward in time, the density, temperature, and energy levels reach a point where a singularity could form, and the normal laws of physics break down at approximately 10 superscript 3 seconds. At these timescales, small distances, brief durations, and high-energy scales defy our understanding. Rewinding the cosmic clock to the speculative zero point at the beginning, a complex historical process would be expected. If the universe started as hot and dense, then expanded and cooled, enormous quantities of particles and antiparticles would have been created, with excess particles annihilated by radiation as temperatures dropped. The breakdown of the electroweak and Higgs symmetries leads to the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons resulted in the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions experienced growth due to radiation pressure followed by gravitational collapse, leading to the formation of large-scale structures about 380,000 years after the Big Bang. The universe cooled sufficiently for stable neutral atoms to form, marking a critical step where photons decouple, with frequencies increasing as the universe expands. The discovery of the cosmic microwave background several decades ago solidified the theory of the early-stage Big Bang as the most supported explanation for the universe's creation. While most space experts and astrophysicists embrace the Big Bang, passionate supporters of the steady-state theory, like Fred Hoyle, continued to defend increasingly unlikely claims, only to face defeat in the face of overwhelming evidence. The evidence presented was clear. It wasn't fading starlight, nor was it reflected or emitted heat from dust. Every possible explanation fell short. The cosmic glow spectrum showed an astounding consistency in all directions, resembling an ideal black body, yet it had no connection to known objects in the universe. Regardless, Hoyle and his supporters continued obstructing scientific progress by advocating experimentally shaky positions. Even as the academic community moved toward the Big Bang as the consensus, the skeptics lost ground, their flawed efforts fading into obscurity. Meanwhile, the fields of space science and astronomy experienced remarkable growth from the 1960s through the 2000s, with cosmology undergoing exceptional expansion during this period. We mapped out the vast universe and described its structure on a grand scale. We delved into the development, evolution, and dynamic interactions of galaxies and their stellar populations. However, despite these advances, we encountered anomalies that defied explanation within the framework of the Big Bang theory. Observations revealed inconsistencies that challenged the predictive power of the Big Bang model, most notably the absence of expected relics, such as magnetic monopoles or particles from grand unification. The universe we see today appears to require forces beyond our current understanding, yet these remain elusive. At its inception, the universe required a precise rate of expansion to balance the total energy density, a feat that the Big Bang theory struggles to justify, achieving equilibrium or allowing sufficient time for energy exchange across different regions of space. These oddities present significant challenges for cosmology and the scientific community as a whole. When theories fail to account for observed anomalies, two approaches emerge: refine existing theories or consider alternative explanations. The theory of inflation emerged as the most promising theoretical framework for extending the Big Bang perspective. Inflation proposes a period of rapid expansion, smoothing the universe and enriching it with uniform properties. It solves the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. Inflation's predictions align with observed patterns and variations, bolstering its validity. While alternatives exist, inflation's scientific power remains unmatched. Despite previous contributions to general relativity and singularities, Roger Penrose's work, including his collaboration with Stephen Hawking, failed to match the success of inflation in explaining the universe's earliest moments. Recently, there has been deliberate work to undermine the validity of inflation theory, instead supporting conformal cyclic cosmology, which is inherently flawed from a scientific standpoint. The key distinction lies in their predictions. Conformal cyclic cosmology suggests that remnants from a universe preceding the Big Bang are embedded in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflation theory maintains that the point where inflation ends and a hot Big Bang begins should be causally disconnected from any pre-Big Bang region. Each part of our universe shows unique characteristics, suggesting that we should rely on the universe itself to reveal what is true, rather than merely depending on theory. Despite initial astonishment, cosmologists quickly identified anomalies in the images sent by the James Webb Space Telescope. Since 2022, these discoveries might require a reassessment of key aspects of the universe's origins and evolution. One major revelation made by the Webb telescope was the presence of fully formed galaxies much earlier than expected by the standard model of cosmology. This anomaly challenges the established sequence of events post-Big Bang, where stars and black holes formed first, followed by the development of galaxies. Such discoveries disrupt our understanding, much like encountering grandparents portrayed as children in a story. Moreover, recent evidence has uncovered inconsistencies within the core hypotheses of the universe, such as the ongoing discrepancy in determining the Hubble constant, which persists despite improvements in data accuracy and collection methods. Additionally, new data from the Webb telescope exacerbates existing challenges to the current cosmological model. These issues highlight flaws within the model itself, leading to doubts among astronomers and physicists. While the model has undergone changes over the past 50 years to align with emerging data, some argue that these changes have been too convenient, prompting growing recognition that a paradigm shift might be necessary, potentially reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human understanding, emerged from Edwin Hubble's pivotal discovery of the expanding universe during the 1920s. Subsequent discoveries, like the cosmic microwave background radiation in 1964, confirmed the theory of the universe's beginning, describing the early universe as a hot, dense soup of subatomic particles steadily cooling over time. However, achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. Cosmic inflation, proposed in 1981, was introduced to resolve anomalies in earlier Big Bang models, further highlighting the dynamic nature of cosmological theory. According to this theory, the early universe underwent rapid, remarkable expansion for a brief period following the Big Bang. While some issues are resolved by this idea, new challenges arise, especially considering the common belief in the existence of one universe and the possibility of countless others beyond our observational reach. Certain observable anomalies, such as hypersingularities within black holes, find support through indirect evidence. However, the puzzling revelations of the Webb Space Telescope regarding the arrangement of universes and the ongoing issue with the Hubble constant rays concerns that we might be approaching a tipping point where a significant overhaul of our current cosmological model becomes necessary. This could require a reassessment of the fundamental building blocks of the universe, including the nature of existence itself. Cosmology, unlike many other scientific fields, deals with broad questions about the universe, its origins, and the role of observers within it. The study of consciousness and quantum physics addresses closely related subjects, exploring the intersection of theory and science, grappling with fundamental assumptions that underpin our understanding. Testing assumptions, such as the constancy of physical laws over time, has been proposed by scholars like Roberto Mangabira Unger and physicist Lee Smolin, who suggest that physical laws may evolve and change over time, challenging traditional views. Physicist John Wheeler even proposes that every observation can impact the universe's past and future, fundamentally reevaluating scientific practices. It is crucial to examine these essential assumptions, given the impact of theoretical assumptions on data collection. History has shown that shifts in scientific thought, such as heliocentrism, evolution, and relativity, have led to profound changes in cultural perspectives. A similar impact on our consciousness might be expected from any impending scientific upheaval in cosmology. Scholar Robert Crew argues that theory becomes essential when further scientific inquiry fails to provide satisfactory answers to a scientific question. The ongoing debate focuses on whether theory is needed to address the cosmological fundamentals. If modifying existing models proves inadequate, a complete overhaul of our understanding of the universe may become necessary, accompanied by new narratives to convey these shifts in perspective. Advances in observational technology have revolutionized our understanding of the universe. The James Webb Space Telescope, with its cutting-edge instruments, allows astronomers to peer further back in time than ever before, capturing light from the early universe that has traveled billions of years to reach us. This ability has transformed our view of cosmic history, revealing patterns and anomalies that challenge long-held beliefs. One of the most significant implications of the Webb's discoveries is the potential for reevaluating the timeline of cosmic evolution. For example, the discovery of mature galaxies just a few hundred million years after the Big Bang raises questions about the speed and nature of galaxy formation. This observation suggests that the processes governing star and galaxy formation may have been more complex and efficient than previously understood. The implications of this challenge assumptions about the ongoing evolution of cosmic structures and suggest that large-scale star formation may have occurred much earlier than current models predict. Furthermore, the detection of surprising patterns in the cosmic microwave background radiation, combined with data from the Webb telescope, indicates that our universe may be more homogeneous and isotropic than the Big Bang model can fully explain. This has sparked discussions about the possibility of a multiverse, where our universe is just one of many, each with its own distinct properties. Such a paradigm would not only redefine how we understand physical laws but also redefine the boundaries of scientific inquiry, as we may no longer be able to directly observe other universes. As astronomers continue to analyze the data from Webb, the potential for finding exoplanets in habitable zones around distant stars has reignited interest in astrobiology. The study of atmospheres from these exoplanets could yield insights into the chemical signatures of life beyond Earth. Researchers are especially interested in identifying biomarkers, substances that could indicate the presence of biological processes. This search could ultimately lead to significant philosophical questions about our place in the universe and whether we are alone in the vastness of space. Additionally, recent discoveries from Webb have prompted a reassessment of dark matter and dark energy, two of the most mysterious components of our universe. The anomalies observed in universe rotation curves and the distribution of large structures may suggest new connections or particles that differ from existing theoretical models.